All right, let's go back to page 33 and talk about this stuff on the bottom. Noble gas configuration, that's what that NGC, stands for. NGC, noble gas configuration. This is a shorter shortcut. So orbital notation was this big giant diagram. Electron configuration was where we shortened that diagram. And noble gas configuration is where we take this electron configuration and cut it down even shorter. Basically what we do is we replace some of the electron configuration by putting the symbol of a noble gas in brackets. And when we put that noble gas in brackets, that indicates all the electrons in those orbitals up to the noble gas have already been filled. So it helps if you know the noble gases are this column, the very last column on the periodic table. And if you look at the periodic table at all your noble gases, helium has 2 electrons, so its electron configuration would be 1s because it's in the 1s section, 2 because there's 2 electrons there. Neon lands in the 2p section, so its electron configuration starts at 1s, has both of those electrons, moves to 2s, has both of those electrons, moves to 2p, has all 6 of those. So neon, as it says on your paper, would be 1s2, 2s2, 2p6. And so on and so forth with the other noble gases. You don't have to memorize these. You can just know where the noble gases are on the periodic table, and you can make yourself a shortcut, because here's how this works. We look at, like, carbon. Carbon is 1s2, 2s2, 2p2. And we can substitute, instead of writing all of this, we can say, well, 1s2, that's the same thing as helium. So instead of writing all of this, I can just write helium for that first part in brackets. You have to put it in brackets. And then this last part that's not helium, that is just carbon. So I can tack that on. And I know you're looking at that and you're going, Ms. Rosinski, that is not significantly shorter. Well, my page has a typo. It's probably fixed on your page. When we get to something like sodium, it can be a lot shorter, because sodium I look at and I go, okay, 1s2, 2s2, 2p6, 3s1. Well, neon is 1s2, 2s2, 2p6. So instead of writing all of this, I could just write neon in brackets. And then this last part that's not neon, the 3s1, I just tack that on the end. So those parts that are not part of the noble gas, you still have to write. But that first part that is the noble gas, you can just write the noble gas instead. Same idea when we get to, like, chromium. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d4. That's a lot of stuff. You could go through this whole list of your noble gases to try and figure out which one covers it. There's actually probably a faster way to do it. If you can find chromium on the periodic table, what you can do is go backwards through the elements, backwards by atomic number, until you hit a noble gas. So like chromium's number 24, go backwards, number 23, number 22, number 21, number 20, number 19. When I get to number 18, oh, this is a noble gas, argon. So argon is going to be the noble gas that I substitute in to shorten chromium with. And, you know, if we look at argon, argon is 1s2 through 3p6, so that tells me all of this stuff is argon, and I don't have to actually write all of that. I can just put brackets and argon, and then just this extra stuff, 4s2, 3d4, I can write, instead of having to write all of that, 1s2, 2s2, 2p6, 3s2, 3p6. Instead of all that, I can just write argon, and then this leftover bit. And again, same idea when I get to gallium. I can shorten gallium by substituting in a noble gas. And if I want to shorten it the most possible, then I got to know which noble gas to pick. So again, I can go to my periodic table. I can find gallium, number 31, and just go backwards till I hit a noble gas. So gallium's 31, 30, 29, 28, 27, 26, just counting down till we get a noble gas. 19, oh, 18, there's a noble gas. We're looking at argon again. And if I know I'm going to substitute in argon, and I want to know how much of gallium is argon, without maybe having the benefit of this little list to look it up in, you could just like look at your periodic table. Argon is in the 3p section, and it's element number 1, 2, 3, 4, 5, 6. That means argon ends at 3p6. So instead of writing all of this from the beginning through 3p6, that is what I'm substituting in argon for. And then this leftover bit, 4s2, 3d10, 4p1, that's the only part extra that I still have to write. So having talked about that, let's try it on these same practice problems we've been looking at on page 34. So we'll try it for boron, neon, and iron. Boron, 1s2, 2s2, 2p1. If I want to write the noble gas configuration, I need to find the noble gas that I can substitute in. So I'll go to my periodic table. Boron's element 5. I'm going to go backward till I hit a noble gas. Number 5, number 4, number 3. None of those are noble gases. But number 2 is. That's helium. So I know that for my noble gas configuration, I'm going to be substituting in helium. So the first thing I do is I write helium in brackets. Then I have to figure out how much extra stuff do I still have to write after helium. Well, we know that helium is in this 1s section, and it's element number 1, 2 in that 1s section. So that means just this 1s2 right here, that is helium. And this other stuff outside of 1s2, that's the part that's not helium, that's the part that's just boron. So that's the part I have to make sure I still write over here. We can look at neon the same way, where with neon, I still have to go backwards to pick my noble gas. I know neon is a noble gas, but you can't just write neon in brackets. Sorry, you have to go backward. So 10, 9, 8, 7, 6, 5, 4, 3. Nope, nope, nope. Oh, but element 2 is a noble gas. That's helium. So I'm going to start by putting helium in brackets. And then again, I have to figure out how much of this is my extra stuff that I still have to write. Again, if I look at helium on the periodic table, I know that helium is still in the 1s section, and it was element 1, 2. So from the beginning to 1s2 is the part that is helium. So this part is helium. This part's my extra that is just neon. So that's the part that I have to continue to write. And same idea, let's look at iron. Find iron on the periodic table. Go backwards till we hit a noble gas. 26, 25, 24, 23, 22, 21, 20, 19. None of those were noble gases. Go back to 18. Argon. Our buddy argon. Argon is AR. That's the first part I'm going to write. And then I have to figure out how much of all of this junk is argon and how much is just the tiny little extra part that I have to add on to make it be iron. Well, if I look at the periodic table, argon is in the 3p section. And it's number 1, 2, 3, 4, 5, 6. So if I start at the beginning and go through 3p6, that is the part that is argon. And this leftover junk is the part that I still have to write. Okay, so at this point, you should be able to finish most of page 34 and 35. I'm going to have you pause the video and work on the noble gas configurations. And when you come back from unpausing, we're going to do one more thing in this video. So try your noble gas configurations for all these elements while the video is paused. All right, and at this point, if you have unpaused the video, go to page 36. If you have unpaused the video, go to page 36. Page 36 is about Lewis valence electron dot structures. Dot, 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 dot. We put 8 dots there because sometimes you draw up to 8 dots. We're very clever. Lewis valence electron dot structures show the symbol of an element and its number of valence electrons. That is a word you may remember from middle school. The valence electrons are the electrons in the outer energy level of an atom. So like if you're looking at an atom, here's your nucleus, and it's got some electrons out here, and it's got more electrons out here. The ones in the furthest outside, those are your valence electrons. Valence electrons are integral, that means very important, in determining how the atom will chemically react with other atoms. We can use some steps to draw a Lewis valence electron dot structure. First, you write the element symbol. That symbol represents the atom's nucleus and the inner electrons. You could also call those the core electrons. Then you determine the valence number for that element, which will be the same as the column number. The column number indicates the number of valence electrons. And you put a dot every 90 degrees until the number of valence electrons present in the atom is achieved. You should never have more than 8 valence electrons. Never. So, here's how this works. Like carbon. Its group number, groups are what we call columns on the periodic table. We'll talk about that more in Unit 5. Columns are the vertical ones, up and down. Carbon's group number, we find carbon on the periodic table. Its atomic number is 6, but its group number is 4 up here. So that 4 is what we're looking for. Group number is 4. That means there are 4 valence electrons. So to draw the dot structure, I draw a carbon. I pick a side, I put a dot. And I put a dot every 90 degrees until I have the number of valence electrons, which is 4 for carbon. So I go 1, 2, 3, 4. Just moving around 90 degrees. Easy. Okay, for fluorine. Its valence number is 7 up here. Its group number is 7. That means its valence number is 7. So what you do is you put a dot every 90 degrees, 1, 2, 3, 4. Then you have to go back around and pair them up. So 5, 6, 7. Not so bad. Hydrogen. It's in group 1. So it's going to have 1 valence electron. So I draw the H for hydrogen, and I just stick 1 dot on it, and I'm done. Aluminum. It's in group 3. Neon is in group 8. So aluminum is going to have 3 valence electrons, neon's going to have 8. So aluminum, I go 1, 2, 3, and I stop. neon, 1, 2, 3, 4, and then you go back and pair them up, 5, 6, 7, 8. There are wrong ways to draw these. Okay, there are several very wrong ways to draw these that you should not do. Okay, for instance, don't draw any that look like this, where you have more than 2 dots on each side. You should never have more than 2 dots per side. Okay, another way you could draw it wrong is if you draw 2 dots on each side and then you have empty sides. There should never be an empty side if you have some paired up. And the other way that's like really annoying to me to watch is people go, okay, neon needs 8, 1, 2, 3, 4, and then they come out and like spin it around like this. Don't do that. Those electrons are going to be attracted to the nucleus, so they're going to get as close to the nucleus as they can. So drawing it where they're suspended out like that is terrible. Don't do that. You can use electron configuration to find the valence electrons. So to the right, we're going to draw or write the electron configuration for arsenic. Then we're going to highlight the valence electrons and draw the Lewis structure. Arsenic is down here in the 4p section of the periodic table. So we're going to have to start at the beginning, 1s, and we're going to have to move all the way through to arsenic. So we start at 1s and go across. There are going to be 2 in the 1s, so I'm going to write 1s2. You might want to write this small or you're going to run out of room. 1s2. After that, we're not to arsenic yet, so we go to the next row. Now we're in the 2s section, so I'm going to write a 2s. How many elements are in the 2s section? 1, 2, so I'm going to write a 2. Not to arsenic yet, so I go across. Now I've hit the 2p section, so I'm going to write 2p. How many elements are in 2p? There's 1, 2, 3, 4, 5, 6, so I'm going to write a 6. We're not to arsenic yet, so I go down to the next row. Now we're in the 3s section, so I write 3s. How many elements are in 3s? There's 1, 2, so I'm going to write a 2. Not to arsenic yet, so I go across again. Now I'm in the 3p section, so I'm going to write 3p. How many elements are in the 3p? 1, 2, 3, 4, 5, 6, so I'm going to write a 6. I'm still not to arsenic yet. Arsenic's all the way down here, so I got to keep going. Go to the next row. Next row is 4s, so I'm going to write 4s. How many elements are in the 4s? There's 1, 2, so I'm going to write a 2. Still not done. Next section is 3d, so I'm going to write 3d. How many are in there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Put a 10. Still haven't reached arsenic yet, but we're almost there. The next section is the 4p section. So I'm going to write 4p. Now arsenic is in this section, so I don't need all 6. I just need how many it takes to get to arsenic. So that's 1, 2, 3. This is 4p3. Okay, and what was the point of doing that? Well, here's a cool trick. You can figure out the number of valence electrons by looking at the electron configuration if you know what you're looking for. So the directions say highlight the valence electrons. Okay, the valence electrons are going to be the electrons in the highest, or we could say biggest, energy level. So for arsenic, the energy levels would be those like big front numbers, right? So for arsenic, I've got 1, 2, 2, 3, 3, 4, 3, 4. The highest energy level is this 4th energy level here. So all those electrons that are in the 4 sections, so the 4s2 and the 4p3, those are your valence electrons. 2 plus 3, guess what? That's 5 valence electrons. And I should draw 5 dots. 1, 2, 3, 4, 1 on each side. Then you go back and start pairing them up. And if you double check, surprise, arsenic is in group 5, so it should have had 5 dots around it. Good job. Go team. Let's look back at page 34. And we're going to try this for boron and neon and iron. Boron has 5 total electrons, but the valence are these right here. 2 and 2 are the biggest front numbers, so these electrons right here, these 2 and this 1, those are your valence electrons. So we're looking at 3 valence, which again I could confirm just by checking my periodic table. Boron's in the 3rd group. 3 valence electrons means 3 dots, so I just draw 1, 2, 3. Looking at neon. Neon's valence electrons, again, it could be 1, 2, or 2. The highest is 2. So all the ones in these 2 sections are valence. That's this 2 plus this 6. 2 plus 6 is 8 valence. So I need 8 dots. 1, 2, 3, 4. Then we go back around. 5, 6, 7, 8. Now, again, you could have checked that on your periodic table. Neon is in the 8th group, so it should need 8 dots. But when we get to iron, we have a problem, which is that iron's group does not have a column number. You can't use the periodic table to figure out how many valence iron has. You have to use this other trick. So we look at iron's electron configuration and look for the front number that has the largest. So 1, 2, 2, 3, 3, 4, 3. What's biggest out of all of those? 1, 2, 2, 3, 3, 4, 3. What's the biggest? 4. These 2 electrons are the only 2 valence electrons. So iron gets 1, 2. Okay. On pages 34 and 35, you need to also add dots all the way down on all of these. Draw your dots all the way down. And real quick, let's go to your stamp page. I will point out that we had finished the Unit 3 stamp page, so in your book, this is on one side, you need to flip it over to your new stamp page. And this new page is going to be our page for Unit 4. By now, it is probably the 12th and 13th would be my guess. 12th if it's an A day, 13th if it's a B day. You know, if those dates are not correct, then oh, sorry, not September, October. Sorry. October 12th and 13th. If those dates are not correct, you know, feel free to correct them. But I'm pretty sure by now it's probably the 12th and 13th. And you're going to get a stamp for finishing, including all the dots that we just talked about, having pages 34 and 35 totally done. And if you're already more or less finished with that, I'll go ahead and tell you that page 37 is also going to be a stamp. And some of you will get to that on the same day, either the 12th or 13th. So if you finish this first stamp, go ahead and start working on page 37 as well. And at this point, I'm going to pass it off to Miss Woodlock.